moving on with the notes that we started for the velocity versus time graphs. We're going to just finish up this section of notes. So to determine the position, find the area between the graph and the time axis up to that point. So you'll notice with this one, our graph is a little bit funkier compared to the ones that we were finding the area on before. So often it's actually easier to just find the area of the different sections of the graph and then add them together afterwards. So this graph can actually be broken up into 4 different sections. Okay, so if we were to break them up into sections, we have a section here. So this would be A1, area of the first one. We have a section here, A2. Okay, we would have a section here, A3, and then we have this much larger section at the end, which is A4. Okay. So the important thing to note though is that the area is negative underneath the time axis. So we need to just make sure that whenever we're doing A3 and A4 that we are times our velocity, which is 20 meters per second east. Okay, so area of 1 is 600 meters east. Okay, for area 2, we're going to use the 1/2 base times height to find the area of the triangle. So we're going to have 1/2, and then we went for another 30 seconds. And our height was 20 meters per second east. Okay, so our A2 is going to end up being 300 meters east. Okay, for area 3, we again have a triangle, so 1/2 base times height. So we're going to have 1/2, it's another 30-second increment, times, and we're going to change it to east. So it's going to be negative 20 meters per second, or we're going to keep it to east, I guess I should say, instead of switching it over to west. Okay, so we'll find that A3 is negative 300 meters east. Okay, and then for area 4, we're just doing length times width. Oops. Length times width. And so our length is a total of 70 seconds. Okay, times our width, which is negative 20 meters per second east. Okay, and so we should find that A4 is negative 1,400 meters east. Okay, so using the areas to determine the position of the object after these different times. Okay, so after time of 30 seconds, so our position, our displacement, after t of 30 seconds equals basically just A1, right? So if we look over, okay, after 30 seconds, it's just A1 that we have to add together. Okay, so that means that our total displacement of t equals 30 seconds is just 600 meters east. Okay, for 60 seconds, Okay, we're going to add both the area of A1 and A2. So we're going to add A1 and A2 together. So it would be the position at time 60 seconds is A1 plus A2, which is 600 meters east plus 300 meters east equals 900 meters east. Okay, for the next one, 90 seconds, looking back at the graph. Okay, now we're going to add the three different areas together, A1, A2, and A3. Where's A3? A3. Okay, so we're going to have that D at T of 90 seconds equals A1 plus A2 plus A3, okay, which is 600 plus 300 plus negative 300 meters east. So we end up with just 600 meters east. Okay, and then for the last one, the total distance displacement, okay, we're going to have the addition of the last part here. Okay, so adding all of them together, we can kind of shorthand and take the answer from last one. So the displacement of t equals 160 seconds equals, we're taking the answer from the last one, so displacement at 90 seconds plus A4. Or you could have done A1 plus A2 plus A3 plus A4. So we're going to have 600 meters east plus negative 1,400 meters east. And so we'll get negative 800 meters east, or a better representation of this answer would be 800 meters west. Okay, so using the upper and lower bounds of the position as a guide for determining a scale for the position time graph, label key positions at times 30, 60, 90, and 160 seconds. Then consider the shape of the position time graph. Give the motion in these sections. Should you use straight lines or parabolas? Okay. So first we have at time 0, we would be at 0, position 0. Okay, at time of 30 seconds, we found that our position or displacement was 600 meters east. So we need to get our units. So meters east is going to be our positive. Okay, so for 30 seconds, we're going to have, so I'm going to go ahead and label these. So for every 2, I'm going to jump 250. So 50, and then 1,000. And then same down here, 250, 500, 750, and then 1,000. Okay, so at time 30 seconds, we were at 600, so just shy there. Okay, at time of 60 seconds, we were at 900. So at 60 seconds, we were at 900, so about there. Okay, and then at time 90, we were at 600 again. So time 90, 600. Okay, and then for time 160, we were at negative 800. So negative 800, so just past the 750. Now, when trying to consider the shape of the position versus time graph, we have to look back at the motion so that we see if we need to use straight lines, meaning constant velocity, or a parabola, meaning changing velocities or acceleration. Okay, so between time 0 to 30 seconds, okay, so this area right here, okay, between that time, velocity was staying constant, right? It was a constant 20 meters per second. And so for that part, we're going to have a straight line. So I'm going to color code mine just so that it's easier for you to tell, because it's going to be kind of harder to tell that my line is straight. So green is for straight. So from 0 to 30 seconds, we have a constant velocity. Okay, thus it's a straight line. All right, continuing on from 30 to 60 seconds, if we look, okay, we're slowing down. Oh, we're slowing down here, okay? So we're going from 20 meters per second to 0 meters per second. So we're decelerating. So during this time, and I probably should have changed the color. We'll make it pink. So during this time, we are decelerating, meaning that our velocity is changing, it's slowing down, so it's going to be a parabola. So here's a representation of a parabola, okay? From 60 seconds to 90 seconds. So from 60 to 90 seconds here, we're speeding back up, but in the opposite direction, right? The velocity is changing. We're going from 0 to 20 meters per second. So we're speeding up in the opposite direction. So between 60 and 90 seconds, we are accelerating in the negative direction. So again, it's going to be a parabola. So parabola. Okay, and then from 90 seconds on, so from 90 seconds to 160 seconds, if we look back, we have at this portion right here, okay, we have constant velocity at 20 meters per second, so it's going to be a straight line. So we have constant velocity, so it's going to be a straight line. Like I said, I'm color coding mine because it's pretty hard for me to make a straight line on my iPad. Okay, so going over just the velocity versus time graph summary. Okay, some of the key terms is that the velocity versus time graph, it's going to show the velocity of the object at a given time. Okay, and then we also know that the area between the graphed line and the time axis gives position. Okay, and so if we have our velocity time graph, okay, this would be the area we would find in order to find position, and then just note that this is negative whatever direction is given on the actual axis. Okay, as far as equations, we have the slope equation. We know that the slope for the VT is acceleration. So we have our final velocity minus our initial velocity all over our final time minus starting time. Okay, this can also be interpreted into change in velocity over change in time. Okay, and then some other equations that are also helpful are our area ones. So the area of a square or rectangle is length times width, and then our area of a triangle is 1/2 base times height. Okay, so for these diagrams, we're going to describe how the slope of the velocity relates to the acceleration. Okay, so for this first one, we're going to draw a horizontal line. So for our V and T graph, this. Okay, so the horizontal line means constant velocity. Okay, our slope is 0, which means that there's no acceleration, or acceleration is 0. Okay, for this next one, okay, lines with positive slope means that our velocity is increasing in that particular direction. Okay, and so it's accelerating in the positive direction. All right, here where the graph crosses the x-axis, this is a change in direction. Okay, the object comes to a stop. Okay, because that is a velocity of 0, so that would be stopped. Okay, and then lastly, if we have negative slope, the velocity is increasing in the negative direction. Okay, and that's if it's below the x-axis. Okay, so the object is accelerating in the negative direction. So here, for this portion right here, where we start above, it's going to be decelerating, and then these portions are going to be accelerating. Okay, so they're accelerating or speeding up, and then the pink line is decelerating because we're going from a higher velocity to stop, and then below, once it gets below, we're going from a stop position to a greater velocity but in the negative direction.